Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Ilya Levitsky. Ilya Levitsky received his bachelor and master degree in applied mathematics and physics from Moscow Institute of Physics and Technology in 2010 and 2020 respectively. Currently, he is a researcher in wireless networks lab of IEEE and he is working towards his PhD degree. Ilya has created first ever physical prototype of normal Wi-Fi device and have a dozen of papers and patent applications. Currently, Ilya is a voting member in IEEE, the 2.11 working group, which standardizes Wi-Fi technology. Today, Ilya is going to tell us about new direction of Wi-Fi standardization. Ilya, the floor is yours.
Thank you, Vyacheslav. I'm very happy to see you all on my talk. And today I will speak about enabling light communications in Wi-Fi with IEEE 802.11 pp, which will be a new IEEE standard amendment that will potentially be a foundation for future Wi-Fi technology. And before I continue, could you, Vyacheslav, please verify that my sound and all my screens are working okay?
Yeah, all working fine.
Great. So let me go on then. So I mentioned Wi-Fi, but in the name of the presentation, you were promised something about Wi-Fi. So why we're talking about Wi-Fi suddenly, and what is the difference between Wi-Fi and Wi-Fi? What is Wi-Fi in the first place? So Wi-Fi, I assume that some of you may have heard about it in the past. And in short, Wi-Fi is a sort of Wi-Fi version, but which works in visible or infrared spectrum. Wi-Fi, analogous to Wi-Fi, can be translated as light fidelity. And it was first called by a guy named Harold Haas, a co-founder of the company called Pure Wi-Fi, at his TED Global Talk in Edinburgh back in 2011. Wi-Fi is a wireless communication technology which utilizes light to transmit data between devices. And by light here, I mean not any possible electromagnetic radiation, but specifically visible light, and most commonly infrared light, and sometimes ultraviolet as well. So to be specific, Wi-Fi is often understood not as any optical wireless communication technology, but rather the one on a local scale to create so-called wireless local access networks, like Wi-Fi. For that, light sources can use light-emitting diodes, or LEDs, and that differs Wi-Fi from, for example, terrestrial point-to-point free space optical systems, or FSOs. Those FSOs typically use narrowly focused lights, and we usually do not call FSOs Wi-Fi technology because they use lasers, and in Wi-Fi we typically use LEDs. So what is the most tempting thing about light communications and Wi-Fi in particular? Well, two things. First, it is unlicensed spectrum, and second, it is very big unlicensed spectrum. If you were to count from the infrared, which is at approximately 1,000 nanometers, till the violet at 380 nanometers, you would get an astonishing 530 trillion hertz. And that actually sounds like we are on our way to terabit communications, but there is a caveat, and LC is not that amazing. We cannot do hundreds of terabits per second, only hundreds of gigabits per second with our current technology, but that is already something to fight for. And the reasons of this shift from terabits to gigabits, why cannot we have that much rate, is something that I will explain a bit further. But still, 100 gigabits seems fascinating. So the second tempting thing about light communications is something that was announced by Hautas during this presentation, is that LED lighting infrastructure is very common in our worldwide, and it can be reused for Li-Fi purposes. This is such a wonderful idea that whenever you go in your home, you can have yourself a high-speed connection just because there is light turned on. And in my opinion, this is a very inspirational idea, and it is the key primary propeller for the technology developers. Going forward, Li-Fi is claimed to be a very energy efficient technology. So if you compare to RF, in RF devices actually emit radio waves, and that requires energy. In light communication, on the other hand, the devices usually already use LEDs just as lighting, whether you transmit data or not. So the energy is spent only on controlling the light. And as we will see further, that requires much less energy than in RF. And moreover, if you do not need lighting at a specific time, you can dim the lighting a bit lower, spend even less energy, and still have an ability to transmit data. Next, light is a useful wireless medium because it does not cause any electromagnetic interference. This is especially valuable for several infrastructure cases like factories or laboratories or medical environments where radio signal can disturb the work of equipment or can cause noise in the measured data, for example. Finally, light does not pass through walls. And that might sound like a downside, and in fact it is, until that is us and not some intruder that wants to get to the signal. So LC can provide better security for wireless links compared to RF. So what applications can benefit from using Li-Fi? Well, applications that require hundreds of megabits per second or several gigabits per second, or that require microseconds or just a bit milliseconds of latency, those applications surely will. That includes high-speed data transfer indoors for lighting to mobile devices or between two devices, for example. This is also useful for high-quality video streaming, for example, VR applications, as you can see here. And Li-Fi can be also used in EMI-limited environments like factories, labs, or airplanes. So in airplanes, you would not need to switch off your phone anymore or put it in the airplane mode. You can simply continue using Li-Fi without any risks to interfere with the devices in the plane. Wi-Fi is also available in offices and enterprises where each person needs to have a reasonable and secure connection. And we should not forget about vehicle-to-vehicle or vehicle-to-infrastructure communications, where LEDs can not only illuminate the road or serve for basic signaling, but can also be used to transmit important messages along the platoon about traffic accidents or some support communication for driverless vehicles. Moving on, let us talk about how light communications work. And why don't we get our terabits per second? So the biggest difference between light spectrum communication and radio communications is that we cannot modulate a carrier with a frequency of several hundreds of terahertz when our light source is an LED. In radio waves, we can modulate a carrier, and we have special oscillators that generate carrier, but in LEDs, we don't. And neither can we modulate such signals. So the only thing we can change is the light intensity and possibly its color, the color of the light. And here I have graphically shown the transmitter schemes. And here the signal X that depends on time is real, which means that it's not complex, and monopolar, which means that it is positive real function. And it is positive at each time instant. We cannot have negative light intensity. And since the signal is just light intensity and maybe color manipulation, we can take one of two approaches. So the first approach, the easiest one, is pulse-based transmission. Here, the signal is encoded into signal sequence of pulses. And there are several modulation types that rely on this approach, and we will discuss them further. And the second approach is carrier-modulated transmission. And it basically recreates the conventional RF approach, but in LC. LC is light communication. Here, the carrier is induced in the light intensity by modulating the intensity with a sine wave. And since we have a sine wave that serves as a carrier, we can modulate it just as in RF with any well-known modulations. For example, amplitude switch keying, phase switch keying, frequency switch keying, quadrature amplitude modulation at DC offset OFDM. And this is the most complicated thing among the mentioned, and we will talk about it later. At this moment, we can see what limits the bandwidth of the transmissions. It is rate of the components and LEDs in particular. We cannot change the state of LEDs too fast because the signal just will not keep up with the changing electricity current. And moreover, pulse-based transmissions will suffer at high rates because of multipath propagation. So here I have described several ways of how light communications can work. Now the question is, how does Li-Fi work? Which of the two approaches does it take? And the answer is the easiest one. It uses pulse-based transmission. And it enables creating inexpensive chipsets for Li-Fi. And it seems that this factor played the greatest role during the early standardization process. So I said standardization process, but which standards are we talking about? Well, we are not talking about 11BB yet. We are talking about so-called 802.15.7 standard. This is the earliest standard that incorporates light technology for conventional uses, for example, indoors. And I would like to point out that Li-Fi does not operate in full accordance with 15.7 standard in the same way Wi-Fi works in full accordance with 802.11 standard. And this is a bit controversial because on the one side, Li-Fi is firmly associated with 15.7 by numerous researchers. Here you can see some of them. And on the other hand, Li-Fi devices are not that popular on the market. So we cannot take the device and inspect what protocols it uses. And moreover, if someone tries to search a Li-Fi in the internet, they will get very astonishing results like those papers that could achieve up to 224 gigabits per second using visible light communication. This is by this paper. And there is also a project called Ultra Parallel Visible Light Communications, which could achieve up to 3.5 gigabits per second with a single three-colored LED. But none of these rates actually achievable by the 15.7 standard. And which rates can be achieved? Before I answer this question, we have to understand how the standard works and what goals did it set to itself. To begin with, the first version of .15.7 was released in June 2011, and it was primarily focused on, quote, delivering data rates sufficient to support audio and video multimedia services. This aim leads to a set of requirements that can be fulfilled with a basic collection of pulse-based transmission modulations, which are on-off keying, variable pulse position modulation, and color shift keying. To be brief, on-off shift keying basically means that you change the intensity of light between two states, the lower state and the higher state. Lower state is not complete darkness. There is still some light. And LED flickers between those two states very fast and thus transmits some data with zeros and ones. In variable pulse position modulation, the signal consists of several symbols, and in each symbol there is a single pulse which has some position in the symbol. And depending on the position, we can carry some information. And in color shift keying, you modulate your information in a certain color. You want to transmit one big sequence, you use one color, another sequence, another color. So in IEEE 802.15.7, it defines 3 phi layers, not one, the whole 3 layers, phi 1, phi 2, and phi 3. And each of the phi roughly corresponds to a certain modulation type. And as we can see from the table, phi 1 can achieve a bit higher than 250 kilobits per second, while phi 2 and phi 3, their top rate is 96 megabits per second. And to be genuine, that is totally not the numbers I expected to see when I first studied the topic. But as I mentioned previously, the focus of the standard was to support audio and video multimedia services. And nowadays, we have different expectations from light communications. What are they? So to answer that, I have imported this table from a source depicted down below. And we will return to this table in the future, but I want to that you pay attention to those columns in bold. So you can see that we have several use cases, and the throughput varies from 10 or 100 megabits per second till 5 gigabits per second. And of course, 802.15.7 standard cannot achieve those rates. So the standard that was released almost 10 years ago is surprisingly cannot satisfy our needs. It cannot solve our new problems. So in order to go forward, for vendors to produce compatible devices that use light communication and can keep up with our growing needs, it was decided that a new standardization iteration is required, which brings us to modern light communication standards. And there are not one, but 2 standards that are being developed right now. They are 802.15.13 and the topic of my presentation, 11BB. I will just mention an interesting point that both standards are being developed by pretty much the same people, but even though they might sound similar, they actually work in different ways and are focused to achieve different goals. So let me give you a brief information about both. So first, about 15.13, the group that creates this standard started its work in March 2017. And its primary goal was to fix the issues in its predecessor, 15.7. So first, light spectrum was widened beyond visible, capturing a portion of ultraviolet wavelengths and infrared wavelength. The top rate was increased up to 10 gigabits per second, and it still used pulse-based modulations, but it also incorporated some carrier-based modulations. So this standard is primarily focused for industrial purposes and not purposes like we can use at home, like VR, gaming, video streaming, etc. This is for factories, for maybe for some special use cases. But for us regular people to use Li-Fi in our modern lives, we need something similar to Wi-Fi. And this is where 11BB comes. So 11BB alternatively integrates light to 802.11 family into the existing infrastructure for our purposes. So in this case, it is important for 11BB to first provide data rates as high as 5 gigabits per second. Second, meet the stringent requirements of energy efficiency, devices form factor, and their cost. And three, build the standard on top of the existing 802.11 specification. If the third requirement is satisfied, that will immediately mean that the developers and vendors will not need to spend much time on developing the standard and will be able to reuse the existing Wi-Fi chipsets or Li-Fi. And they can be repurposed fully for Li-Fi or can maybe reused for Li-Fi and Wi-Fi for both purposes using in one device at the same time. So let us see the timeline for the project 802.11BB. First, the idea of integrating light communications into 802.11 standards started to evolve in LC topic interest group. And this group has studied technical and economic considerations, including link budgets and broad ecosystem support. Soon, the group transformed into Light Communications Study Group, and its primary goal was to consider possible use cases, and we will talk about them later. And it also needed to identify limitations on the scope of the future task group, sort out the parts which are and which aren't important for light communications, so to change to or not change certain parts of the original 802.11 standard. So next, after the project was approved, the task group 11BB started its work, and its short name is TGBB. And it wasn't until April 2020 they prepared their first draft 0.1. And at this point in time, we have the draft 0.5, and it has a lot of already incorporated mechanics that will be used in the future LC technology in Li-Fi, and we will go over them briefly to understand what could be in the future communication technology. But before that happens, the TGBB group has to refine the standard until it gets to a version 2 or 3 of the draft, 3.0, etc. And after everyone agrees that the standard is complete, and it will be released, and that might happen somewhere in the end of 2022. So here on the slide, okay, so here on the slide we can see that 802.11BB has not approved the draft because it started with 0, and until that happens, it stays in this part of the 802.11 standards workflow. Next, to understand what motivates 802.11BB developers, we need to understand the so-called usage models. The usage models are the ground for the work. They are needed to understand in more detail what do we need for light communication, what for do we need light communication, and what are conditions the devices will work in. So the usage model is not something to be confused with use case. Use case is just one part, one component of the usage model. And it also has other portions. The first one is preconditions. The preconditions take place before the use case begins. The second is environment. And the type or the environment explains the type of place in which the network of the use case is deployed, such as home, outdoor, hotspot, enterprise, metropolitan area, etc. Third, application is a source and sink of wireless data that relates to a particular type of user activity. Examples are streaming video and voice over IP. Traffic conditions is a general background traffic or interference that is expected while the use case steps are occurring. Overlapping BSSs, existing video streams, interference from other sources, those are all parts of traffic conditions. Finally, task-oriented use case. It describes specific step-by-step actions performed by a user or a device. One use case example is a user starting and then stopping a video stream. Let us look closely at one example incorporated in agreed by TGBB, which is called industrial wireless. So the preconditions here are devices may experience unstable RF connection due to electromagnetic compatibility issues, such as jamming in factories. LC is deployed to provide reliable wireless connectivity. The environment is a large metal building, industrial or automated work cell. The area of those environments range from tens to thousands of square meters, and they are typically equipped with industrial robots and some other equipment. The environment is very electrically noisy. For example, MUI radiation from all kinds of noise-generating electronic devices. And lighting level is approximately 150 lux, which is recommended for work, or 10 times more for some dedicated work. Applications are ultra-high definition video streaming for surveillance or production monitoring applications, such as as well as for video collaboration for team, customer, and supplier meetings. And it is lightly compressed UHD video, so it needs ultra-high data rates, ultra-low latency, and ultra-high reliability. And this is something the light communications will cope with. It also specifies the distance ranges between the light communication access points, or APs. So moving on to traffic conditions, here both uplink and downlink use light communications. There can be interference between access points belonging to the same ESS due to very high density deployment. And there can be interference from other surrounding sources like sunlight or other artificial light. Next, multiple LC modules are deployed on robot, on the equipments, on the ceiling and walls to provide multiple light links for robust connectivity in case one single line of sight link is blocked. So we use multiple LEDs and multiple photodetectors to have multiple possible links to operate through. So finally, the use case. Operating instructions are transmitted to the industrial robot via light communications. The robot is working according to the instructions and provides real-time feedback, information, and or video monitoring data for quality control to the control center, also via LC. Upon command, the robot finishes the task and is ready for the next one. So here we have seen one example of usage model, and from this usage model, one can fully understand the scenario and why this scenario is considered and why it is important and all the necessary details. Besides industrial wireless, there are four main usage models, and we will briefly look through them. We will not dive deep into them. Just a few details we'll mention here. So the second model is wireless access in medical environments. And here RF communication is prohibited for MEI issue. So LC is deployed instead. Also, the medical environment is specified, size, the materials, the luminosity of the light sources. And LC is used for telemedicine services and for providing internet or internet connection for staff and patients. All the interference is specified here. And the use case can be a doctor interacting with other staff for assistance or a nurse calling for emergency from a ward. Next usage model is enterprise network. And unlike in previous LC cases, in other usage models, here LC is deployed because of high density of user devices. And RF may not simply deal with it. Also, there can be security and privacy issues, which are solved by light communication. The environment is a meeting room with many seats, and in a meeting room, a UHD video conference may be held, and every participant may need to exchange files with each other during the meeting using also LC. High interference between peer-to-peer networks is expected due to high deployment, and interference from lighting and sunlight may be present. In the use case, the video conference starts, and participants in turn share their desktop. And some people may be walking in the room, sometimes blocking some line of sight paths. The final usage model we will look at here is secure home network. The key preconditions here are the necessity of interference-free environment and the security requirements. That is, the signal will not escape outside the walls or out into the other rooms. So no intruder will be able to access the light signal. As the environment, we will have a living room with some of its own lighting, and here we will expect secure wireless internet access, VR gaming, UHD video streaming, and IoT applications. Use case could be two kids playing VR games together, while their parents perform a mixture of the aforementioned applications. So this table presents a summary of all the usage models parameters and one more usage model backhaul, which is a bit different from those mentioned. Now, having familiarized with the models, one should have a ground understanding, the motivation for each value in the table, and all the necessary details. From this knowledge, one can build a simulation or even set up an experiment according to one of the models and test some light communication solutions. And if someone feels inspired and decides to carry out an experiment or simulation, he would need to build a channel model where he puts all the walls, all the objects, people, surfaces, transmitters, and receivers, and then he extracts the channel impulse response or frequency response using most frequently ray tracing methods. And TGBB has already prepared all of them for each of the mentioned usage models, plus some extra ones, which are gas pipelines, underwater communications, and vehicle communications. So if you would like to use some of these environments, you could check out the references shown on this slide. So having understood the usage models, we can now understand what ideas drive the standard developers From these models, they can derive some requirements for the communication system and propose the corresponding changes. So next, we are going to talk about the current 11BB draft 0.5. And we will see the progress done so far and what is missing right now. Inspecting the draft, one could see that it primarily consists of 5 specifications, and a smaller portion is dedicated to Mac. So we will start with the basic waveform, then we'll go on with the PHYs, and yes, there is not one, but multiple of them. And we'll finish with the Mac features of 11BB. First, the waveform. We have seen this picture earlier, and I explained the difference between creating RF signal and LC signal. I told that there are 2 approaches, using pulses or inducing a carrier and modulating it in any suitable way, including OFDM. But I mentioned that it is not the usual OFDM, but a so-called DC-biased optical OFDM. And basically, the name captures the way the complex OFDM signal is transferred to LC domain. For LC domain, as we remember, the waveform is a continuous light intensity function, which is real and non-negative. But OFDM is a complex function, so what do we do? OFDM should be first transformed to a real waveform, and with the process called upconversion. The way radio signal is upconverted in OFDM is OFDM modulates a carrier, for example, 2.4 gigahertz. The carrier is induced on light intensity. It has the frequency of half of the OFDM signal bandwidth, plus some extra delta. And this delta actually prevents the signal from self-aliasing. So you may remember from DSP courses that a real signal has a symmetrical spectrum, which is shown here. And in this case, the tail of the left-hand side spectrum can interfere with the right part of the body. So delta can prevent that from happening. But delta cannot be too big because, as we will discuss a bit further, the optical channel has low pass filter characteristics. And that means that if we will nudge the spectrum too far, the whole signal will be simply lost in fade. And that is not something we want. So there is a bit of trade-off for this delta parameter. And the next stage is to shift the result by a positive DC component. So we have purely positive light intensity. And that means that we have achieved DC-biased optical OFDM. And here, the effect of PA-PR can have a significant influence if in RF, significant PA-PR causes the tip of the signal be distorted by non-linearities of the filter. Here, they will be simply cut out, and that causes more interference for light communication. So now, as we understand a DC OFDM, understand how it is obtained from regular OFDM, we can understand now the majority of the phi of light communications. So congratulations on that. You already understand the phis. So to be specific, light communication phis take the exact waveform generated by one of the previous RF phis specified in 82.11a, for example, or 82.11ax, and those phis are called OFDM phis and HE phis. And the draft literally says that you could take the waveform generated by one of these phis and apply them in light spectrum. So, but it has some restrictions on the features due to how LC channels behave, and we will go through them in a bit. But the story does not end here. At the start of TGBB, there was a huge debate between two PHY approaches. The quick and easy approach is to adapt the existing PHYs, for example, those ones, almost as is. And that will spend little effort, that requires spending little effort on the specification and reduces the size of the specification and gives the opportunity to reuse existing Wi-Fi chipsets for LC purposes. The other approach is considering the peculiarities of LC channel more carefully and optimize the PHY to make it perform better in a new environment. That would be a so-called LC optimized PHY. And in the end of the debate, the friendship one. So both approaches, the standard ones and the optimized ones, are incorporated in the draft 0.5. But now the question is, what is this new ITUT G9991? What is this, how it works, and we will answer that soon. But let us go through the PHYs one by one so we would understand all of them. First is the common mode PHY, and this is the most basic LC PHY. It is based on the IEEE 802.11a standard, and it is a mandatory PHY. Means all devices need to support it. And it provides basic functionality such as initial association, parameters negotiation, choosing another PHY for further exchange, and some other ones. So in common mode PHY, the data is transmitted only in 20 megahertz bandwidth channels. And the data is coded with binary convolution code at rates presented here. And all OFDMs, OFDM subcarriers use the same noise-resistant modulation scheme. One of those is binary phase shift key and modulation span until 64 QAM. So next, the HE PHY, which is based on 802.11ax standard, is more complex and delivers higher nominal data rates, up to 1.2 gigabits per second in one stream. Moreover, in an LC channel, HE PHY performs better than common PHY. It demonstrates lower preamble error rate, lower bit error rate, and hence lower packet error rate. And the latter one is due to the use of so-called low-density parity check codes. And LC PHY has also a wider set of modulation and coding schemes presented here and supports those types of coding. And bandwidth are similar to those used in 11ax from 20 till 160, and 160 bandwidth can be also split into two portions, just as in 11ax. The optimized or LCO PHY is radically new to the 802.11 standards family, and this is the most exciting one as for me. This family is the family of 802.11 is traditionally used for radio technologies, which adopt bit interleaving coding scheme. And that means that all bits are jumbled across the spectrum and all have sort of the same probability of having an error. But it exhibits a high signal robustness against frequency selective fading, typical for radio channels. But in wireless optical channels, we have, I would remind, low pass filter response. That means that, as experiments have shown, up to 80% of the coded bits will be lost in fade if you use the same MCS for all subcarriers. And LCO takes another approach that I will show on the next slide. So it takes advantage of the technique called adaptive bit loading, and it allows adapting modulation per subcarrier independently. The idea is to allocate more bits, that means use higher order modulation for subcarriers with high SNR, and less bits for subcarriers with low SNR. The transmitter can use either a predefined bit allocation table for subcarriers or a table determined at runtime, which depends on channel conditions. And it was shown that adaptive bit loading provides greater robustness in LC channels, even in the events when the line of sight path is blocked. This is adaptive bit loading technique, and it is already incorporated into the ITUT specification for high-speed indoor visible light communications. So in order not to reinvent the same technique that already works, TGBB sent a liaison, or so to say, kindly asked ITUT to have a chance to copy the portion of their specification. And after ITUT agreed, the LCO PHY appeared in 11BB. So the possible channel widths are as presented here. And the interesting part is the modulation that could be used by subcarriers. So all subcarriers are modulated independently, and they can incorporate from 1 to 12 bits per subcarrier. So if a subcarrier is modulated with modulation with even number of bits, those are square constellations. And if it is odd number of bits, those are either rectangular or cross-shaped modulations. And I think you can find them in the internet. Oh, another interesting feature of LCO is it has natural support for MIMO. And it is a distributed MIMO, and LCO PHY is the only PHY in 11BB that actually supports MIMO. HE PHY does not support MIMO, even though the RF version of it does. So, and we may be familiar with MIMO. With MIMO, a transmitter can use a single stream to a single user to transmit data more resiliently, or use multiple streams for multiple users at the same time. But the details on MIMO are still work in progress. So here I have summarized all the properties of all three PHYs in this table, and you can compare it later when you see the video. So switching to MAC, there are basically only minor features in the sublayer compared to PHY layer. So first, each of the mentioned PHYs requires a MAC sublayer, and MAC should support each of the respective PHYs. For CM PHY and for HE PHY, the MAC would be based on the corresponding MAC from the RF analog. For LCO PHY, the story is a bit non-trivial, because LCO still does not have MAC. It is still in progress. And we will see what features could be used in LCO PHY, in HE PHY MAC. As we remember, HE PHY has introduced OFDMA concept, which means that stays can be served in uplink and downlink in different resource units. And a quick reminder that resource units are portions of the spectrum, which can be allocated to different users. So at one time instant, not one, but multiple stations can be served at different frequency resources. So based on OFDMA in 11AX, there is a mechanism called uplink OFDMA random access, and it will be adapted for LC. So when WARA is turned on in LC, it will work as follows. So the resource unit, which will be dedicated for random access, will be only one. It will be a single resource unit and will be only on the side. So it has a static position, and this change structure, where compared to RF, random access resource units could be anywhere basically. So this change is motivated by the fact that the single access points in light communications are likely not to serve many users, just one or a few. So the efficiency will not suffer very much, but this change will surely ease the processing on the stay side. And also less resources will be wasted. Next, and in my opinion, the most prominent MAC feature of 11BB is relate clear channel assessment. Basically, it is an alternative to traditional CCA from RF. In RF, as you remember, the stay have no strict directionality to signal emission, but LC stays do have. So if one LC stay transmits to another stay, for example, an AP, this signal may well not be detected by some other station because there is something blocking this path, or this path is very narrowly focused. So no signal propagates to this point. So for the other devices, to detect that the channel is busy, the access point does the following. It retransmits in broadcast a signal received in an amplify in forward fashion. So here we can see that the signal is directly retransmitted to all other stations, and those stations can understand that the channel is occupied. And in this scheme, the AP's transmission, either uplink or downlink, will not be interfered by other devices. That concept is already incorporated in draft 0.5. The next MAC feature is fast session transfer, and it is actually not new. It is already defined in previous amendments and is used by 802.11ad and 11ay devices that operate in 60 gigahertz band. So the idea of fast session transfer is to allow devices to switch from their main high frequency band to a sub 6 gigahertz band in case of signal blockage. So the 802.11bb will reuse this technique. And finally, the initial intent of TGBB was to include not only fast session transfer, but another feature for the same amendments, 11AD and 11AY, called hybrid coordination function. And this feature actually will create less contention in the environment, leading to more efficient channel use. But at this point in time, draft 0.5 does not say anything about this feature, so I have not included it in the slides. The final topic we'll discuss is a set of open problems. And before that, I actually want to discuss something other with you. So at this point in time, exactly this week, TGBB has introduced some radical decisions. And in my opinion, this is a bit sad story, and I have at the same time little doubts that we will avoid it. So LCO, which I mentioned as the biggest and the most exciting and the most complex feature of 11BB, it was decided that it would be removed in the future drafts. So the reason for that is it turned out to be more complex than it was expected at first. And during the ongoing July plenary, TGBB decided to abandon the LCO file. From the words of TGBB developers, they may return to LCO in the future amendments after 82.11be becomes released. But until then, we will need to wait for some time. So the situation is a bit controversial because LCO has the most open issues associated with it. So does that mean that when LCO is removed, we will have no issues to solve? Of course not. When LCO will come back, we will be prepared and will design some Mac features which are needed, are still needed for LCO. And those Mac features can be any sort of Mac mechanisms. There is a wide variety of research opportunities for this topic. And as soon as Mac mechanisms are prepared, we will need algorithms to control the parameters of the transmissions. And this is whole another area to explore. So I will give you an example. So we have discussed bit loading technique, and it is applied. When it is applied, it uses either a predefined table or a table formed dynamically with a known channel state. So the state needs to feed back the CSI to the or channel state information to the AP, and AP will need that information to choose the table. But there is still no procedure for that. And there are many possible ways to do that. And after the procedure is defined, and the state and AP will need to negotiate the other parameters. For example, the periodicity of the feedback and the precision of the feedback. So here is some trade-off: precision versus periodicity. And very similar problems arise for distributed MIMO in LCO-PHY as well. And I will also mention that instead of LCO, actually, TGBB during this week decided that they will incorporate other PHYs that are present in 82.11 family, in particular HE and EHT PHYs. And for those PHYs, we do not yet have tests that verify their performance in a new medium. So that is something that needs to be done, and the algorithms may need to be changed according to the new medium. And also, the final thing I would talk about is that even though there are some possible PHYs that I have talked about, we may develop new PHYs that could be suitable for WLANs as well as Wi-Fi. And this is a very interesting topic to lead a research in as well. So to conclude, I find this topic very interesting and inspiring, and the idea of light communication is especially bright, and it needs some truly enlightening research. I hope that LC technology will see a great development and attract high interest from people in different areas, including customers like us. And we will use high-speed communications, maybe not as fast as 200 gigabits per second, but still close enough. And I hope that you liked my today's seminar, and I hope that you also have a lot of questions for me to answer. So thank you very much. So I think that we have some questions in chat. So let me see the questions. So Artem Krasilov says, IEEE 802.15 group also develops wireless technologies that use visible light communication, and they also called Li-Fi. What is the difference with technology developed by IEEE 802.11 group? So during my talk, I have already mentioned.
Sorry, yeah, thank you. You have already answered, because I put this question in the early of the presentation, and you have asked it during the presentation. So thank you. We can go further.
Okay, I see. So the next question is from Vyacheslav Loginov. How 802.11bb is going to compete with 802.15.13 in industrial scenarios? You have previously mentioned that 802.15.13 was designed for such scenarios. Well, this is a very interesting question. I think that for 802.11bb devices, the key advantage of those devices is that they can coexist with Wi-Fi devices that already are in wide use, and the devices that use 11bb can enjoy such natural features of 802.11, such as fast session transfer when one of the paths is blocked, for example. But I think that there can be some other points that make 802.11 more interesting in the industrial scenarios compared to 15.13. But eventually it is up to vendors which of the standards they will like the most. So the next question is also from Vyacheslav. Is sunlight interference a problem for PHYs of 802.11bb? Can we ignore it? Or we can use 11bb only when the windows are completely closed? So when you use a light communication device, I don't think that we can detect when the curtains are made or unmade, so when the windows are closed or not. So we need to consider all possible cases. For example, when the light comes into the room and interferes with the communication. And is it a problem? Well, yes, I think that it is a problem, because it is designed to be used at any point in day, in the morning, in the day, in the night, and that means that the light communication will be reliable. If we cannot use it during the sunlight, it means that is unreliable. So TGBB will need to deal with this problem as well. And the early studies show that sunlight is something that can be dealt with. The next question, also from Vyacheslav, is about relayed CCA feature. It seems that to use it, AP must work in full duplex mode. Is it possible in light communication? Because Wi-Fi in RF spectrum use half duplex mode. This is correct. The light communication APs can indeed work in full duplex mode. And the reason for that is the high directionality of light. When we use RF antennas, when we transmit from one antenna, the signal will unavoidably go to the other receiving antenna and cause interference. But in light communication, we can have a detector pointing at one point and a light emitting diode pointing at another point, completely isolated from each other. So even though access point will shine something from the LED, this signal will not be detected by the photodetector. So this is how relayed CCA will work.
Thank you for your answers.
Thank you, Vyacheslav. So the next question is from Mikhail. how is the uplink is expected to operate? The device must use an omnidirectional light source. So I understand that the question is, how would the devices work in the conditions where the user takes, for example, a phone working with light communication, and it has some detectors, and user can rotate the mobile phone in any direction, but it still needs to get the signal from the access point, for example, a lamp on the ceiling. And the answer is that for those kinds of devices, the photo detector on the device will need to have some wide enough aperture for signal to have opportunity to get to the photo detector, as well as the light source, for example, access point, will need to have wide enough aperture as well to get to different devices in the room. And even though light may not go from the line of sight paths, still there is a possibility for communication when the devices are non-line of sight, when they experience non-line of sight scenario. And in this scenario, light communication is possible as well, and it was proven experimentally. So, and what about uplink? So uplink means that devices use light to transmit some data to access point as well. So here I think that it is a bit controversial too. For example, user devices could use multiple different light sources. For example, multiple LEDs used at different places on, for example, mobile phone or tablet or something that you use. And even in cases when all LEDs are blocked for some case, still devices can reuse fast session transfer mechanism and enjoy not that fast, but still some communication. So I think that is how the LC devices are expected to work. Does that answer your question, Mikhail? Okay, I think I will go to the next question then. So the question from Artyom is...
maybe I can clarify. So the question is actually related to the question of Mikhail. So actually, if we look at the light source for the downlink, so we can use a lamp with high aperture with high power. So it has much more power, and the light can go through a high distance and through high area to cover high area. But how the emitters at the device side will look like, because they will have very small size. They should emit low power because it will disturb the user if some LED will definitely change its power. So actually, I see that there is a high asymmetry in the size and in the power of the emitters, which can be put on the downlink side, in the uplink side. So, and of course, this will lead to the asymmetry of the link capacity. So, and how the .11 dB will work with such situation, whether some specific solutions are designed for this problem.
Okay, thank you for the clarification. As far as I remember, this kind of asymmetry is not addressed openly in the TGBB group, but I can assume that the problem you mentioned may be solved by putting photo detectors closer to the user device. For example, having multiple photo detectors throughout your room, and hence having better chances for detecting signals from mobile devices, even though their intensity may be small. And actually the same comes for downlink channel as well. If you move between some places in your home, for example, you would need to have multiple access points, multiple lamps throughout your home to have a stable light communication connection. Okay, so I see one more question. So I guess you can use infrared waves in uplink not to disturb the user. So I think this comment is refers to how bright the signal can be. Is that right? Vyacheslav?
Yeah, it's a comment on the Artyom question, because he asked whether if we have, for example, some LED in your mobile device and it will emit some light, it can disturb the user. And so my comment is that 11dB is also designed for infrared, so maybe we can use infrared in uplink to not disturb.
Yes, that is correct. Maybe I misunderstood the initial question by Artyom at first place. Well, yes, devices can use infrared light, and using infrared has its benefits. For example, the user would not see this light, and it will not disturb them. Also, infrared has different characteristics that compared to visible spectrum. For example, RF typically propagates at a bit further distances, and it can also pass through some materials which look opaque in visible spectrum, but are actually transparent in infrared. So that is one more advantage of using infrared light.
Ilya, maybe one more question from my side. So at the beginning of the presentation, we were talking that the visible light communication is the opportunity to reach hundreds of gigabits per second, like terabits per second. But when we have discussed actual PHY implementations of TGBB, we have seen that actually the bandwidth which is considered is limited by 160 megahertz, 200 megahertz, and the data rates of several gigabits per second. So how we can close this gap between gigabits and hundreds of gigabits per second? So what are the future plans maybe of TGBB to reach terabits? So maybe you can share some.
The answer would be twofold. So the first part of the question, part of the answer is that we indeed were promised by numerous articles that we will be on our way to several hundreds of gigabits per second. And I have already explained why we cannot move on to the terabits, because we need to, then we would need to be able to modulate the light carriers. That is not something we can yet do, except we can use lasers, but in Li-Fi we do not use lasers, we use LEDs. This is the first part of the question. The next part is that during the July plenary meeting, TGBB actually decided that they will not continue their work on trying to push the limits of TGBB up to 5 gigabits per second. They will stay on the level of several hundreds megabits per second at most, and this is again motivated by the fact that the standardization process at this point of time is too complicated to achieve such high rates, and using even wider bandwidths will require to change the existing files in some way, and that means that the Wi-Fi chipsets will not be able to be reused for light communication purposes. But the final part of my answer is that I hope that TGBB will continue its work, maybe under other name, but it will not incorporate incorporate LCO-Fi and MIMO with it, but it will also reuse the concepts of TGBE amendment. And this amendment not only brings higher or wider bandwidths up to 320 megahertz, but also it introduces multi-link operation. And multi-link operation, in my opinion, is the key factor of being able to push our connections up to hundreds of gigabits per second, because you can transmit those OFDM symbols in different colors. And that means that we can have a lot of colors, and each of the color carries its own very wide, very high rate connection. So this is how I see the future of light communications in Wi-Fi.
Oh, thank you, Ilya, for this future view. So actually, it looks like carrier aggregation, which we see in the low frequencies, so in the radio frequencies. So if we have 160 megahertz channels, we can just add one more and more and more channels if we have available bandwidth. So the same approach can be utilized in the light communication.
Well, yes, it can be used, and the limit here is just the clocking rate of the chipsets. And I mentioned that another way to multiply the bandwidth of your connection is to use multiple separate bandwidths, which are located at different portions of the visible or infrared spectrum. And this will basically achieve pretty much the same goal.
Great, thank you.
And don't you have only 3 types of LEDs, like red, green, and blue? Nope.
Yes, that is correct, but you could also add infrared LEDs here. And I think that if you were to use some LEDs for communication purposes, you could, as a vendor, sell some different LEDs and use different photodetectors for those specific spectrums as well. So the first step is, of course, use 3 bandwidths, red, green, and blue, which will already triple the maximum rate. Using infrared will increase that as well, and we can have other LEDs. Nothing stops us from doing that.
Well, I thought that there are some like technology limitations, like that you cannot make the spectrum of a single LED narrow enough so that your LEDs will intersect, in fact. But okay, I don't know, so it's just like a comment.
Yeah, I see your comment. I think this is another possible area of research, identifying how the LEDs of different colors interfere with the photodetectors that are focused on those specific colors. And in my opinion, this task is already being solved by the guys who study some optical effects and how cameras and photographs work. So this kind of area. I think that they know how one type of LED of red, for example, influences the green photodetector. Okay, any more questions?
So I guess that's all. Thank you, Ilya, for your very interesting presentation. And thanks to all listeners for participating in the seminar. So see you next week in the next seminar.
Thank you all once again for your interesting questions, for interesting discussion. See you next time.